So in today's talk, I will share some interesting insights, observations, and techniques about pre-trained model compression. And this talk should be easy to understand and easy to follow, and you guys don't need to have any prerequisites. And if you have any questions during the talk, please let me know, and we can discuss and share opinions. Okay. So for today's talk, our object is to know the basic principles of model pruning and quantization, which is the general used, the widely used model compression techniques, and also understand the ELF is the exponentless floating point number compression. We just proposed a new compression algorithm on pre-trained models, and what motivated us to propose this algorithm and how this algorithm works. So nowadays, can I remove this bar?
You can just drag it to the left or the right.
You can hit more and you can hide it.
Can I hide it?
Hide floating meaning controls.
Hide it. All right, thanks. Thank you. So now if we want to have a model, we will not probably train it from scratch, and we will just go to like a Hugging Face, TensorFlow Hub, such kinds of cloud providers to download a pre-trained model and to deploy to our scenarios, right? Just like we always visit like a GitHub to download, to copy the code. But there is a heavy burden on storage for such kinds of cloud providers. So by the end of the last year, there are more than 400K models on this website, Hugging Face. Right now, for yesterday, it's over 500,000. The developer is so quick, and the storage side it is more than 1,400 terabytes, which is scary. And this is for model storage. Another scenario is for model transfer. So it's like during the federated learning, the client has to download model from the central server every training round. Another simple example, Tesla. In order to use the autopilot, the latest autopilot, we have to download the newly trained model from Tesla. Otherwise, we cannot drive it. It will not allow us to drive the Tesla, the car. So that means reduce the pre-trained model size matters on many scenarios, many applications. I know you guys have a question. How about we just zip it? How about we just throw to the general purpose compressor, like zip, like tar? And the result from our analysis, our experiments shows that this might not be a good idea, because for most of pre-trained models, it only can achieve like 7% footprint reduction. Indicates this ineffective. All right, so we have to deal it by our own. Before we jump into any techniques, algorithms, we have to know what's inside a pre-trained model. If we unfold the model, we can see, for example, AlexNet. We can see different layers over here. Maybe you guys think this is like a rectangle, but if we can just see a layer can be multi-dimension, we can see this as a layer. This is different layers, right? And if we slice a layer, we can see the parameters, the arrays, and we stretch this array, we can get the floating point numbers within that array, that tensor, or we can call it tensor. So now we want to use some existing effective detail reduction methods like deduplication. If we can find that for several layers, they are exactly the same for different models. So that means we can deduplicate such kinds of layers for the different model, which can reduce the model, the footprint, right? But the results from the results from the experiment show that only for these such duplicated layers only account like 5% footprint, which is small. And this method is not promising, right? How about we just split the layer into different fixed size chunk, like 4 KB, like 1 KB, or even smaller. But the result is still negative. So we have to jump into this parameter level, the number level. And we observe that floating 32 dominate whole model parameters, like more than 98% of parameters are floating 32 based. And these numbers and these floating points are within the range -1 to 1. And this is the observation we come up very first. And also there are a lot, yeah. Go ahead.
Before you keep going, when you say deduplication,
Yeah.
do you mean having the parameters in those layers or in those chunks being the exact same, therefore you could just remove one of them and have and point to a pointer that says these are the places where this matches?
Yeah, exactly.
Okay.
Exactly. Yeah. So for the parameter level, and we draw these two interesting observations, and there are a lot of interesting insights and observations, and you guys can refer to the paper we just submitted to the archive. And this paper has been accepted by the VLDB recently. Okay. So it looks like right now we have to deal with such kinds of numbers by our own. I know it is non-trivial. I know it is difficult to handle so small granularity things. Before we go further, let's get a recap on how the computer represents such floating 32 points. So this is a typical representation, right? 1 for sine, A for exponent, and 23 for fraction or mantis. Okay, first we have to know how to calculate model size. So equated model size is the number of parameters times the bit width for every parameter, which is simple, right? Easy. For example, for LX9 has 61 million parameters. All of them are floating 32. The size of the LX9 can be calculated as this one. It's like around 200 megabytes. So, how to reduce model size? Yeah.
Reduce the bit width.
Yeah. That's one technique. Any other one?
Yeah, with parameters.
Yeah. That's two obvious directions we can reduce the model size, right? Or we can just reduce the numbers, or we can just shorten the bit width for every parameter. Let's talk about the pruning. Let's talk about the pruning, which is reduce the number of parameters. We call it pruning. So pruning means like a cut, right? If a tree is like this, we just prune a branch. We cut it. So we remove it. What way or what branch should we remove? Should we cut? For example, here is an input. Here is the weight. 1, 2, 3. With one, 2, parameter 3, and this is the result. What do you guys think? Which way we should remove?
X3.
X3. Why this one?
It has the smallest absolute weight.
Exactly. Yeah.
So why do we need to remove the smaller one?
Is that a question for me?
Yeah.
Okay, if you remove the smallest one, it should have the least impact on the model's prediction performance, and that's how it was trained and evaluated, so that should have the least impact on its performance after the pruning.
That's right. Go ahead.
This is only, I know that we're focused on like AlexNet here, but like making that assumption is assuming that these X's are normalized, right? Which is the case for like a deep network. But like for another model, like if those variables are on a different scale, then just simply removing the lowest weight wouldn't be correct.
Yeah.
Okay.
Yeah. This is the principle. Yeah, we remove the principle is that the smaller magnitude, the importance of the parameter, right? We can just throw it away. We can just remove it. But fortunately, based on our observation, the percentage of these such kinds of like a smaller magnitude parameters account like a certain big percentage. So yeah, we can based on this observation, maybe we can draw some. We can use the pruning get a good comparison. Okay, next is the process of how to prune a pre-trained model. First, we get the model structure, we get the model weights. Oh, guys, just a reminder, just a kind of reminder that we are here talking about the storage side. We are not talking about the training or inference side. If during the training or inference, we don't need to, we don't have to change the storage size of the model. We can just mark here the parameter as 0 into the GPU, right? It's different, but just a reminder. Yeah. So for storage side, we have to get these two things just in later use for recovery. And next, we set a magnitude, and we set the parameters smaller than this magnitude to 0, like this one, like this one. And we remove it. We remove such kinds of zeros. But how can we know which position the 0 is 0 on? And that's an interesting question, right? A simple way is that we use a bitmap. So 0 means this parameter stay, 1 means that this parameter removed. And this is 1 bit for every parameter. And for this one, the parameter, these are floating 32 bits. And then we store such kinds of 3 files, and we done the pruning. Simple, right? And decompression is pretty much the reverse process of compression. Yeah. Yeah.
Is the bitmap that encodes the prune parameters, is that also constrained to 32 bits as well?
You mean how to store such kinds of bitmap?
No, like is that bitmap constrained to 32 bits, or can you have like longer than 32 bits bitmap?
Oh, yeah, that's the bitmap. We can just we can store it by our own. We can just store it like a bytes. Every eight bitmap, every bit, a bit. We can store it.
I get that part, but like I mean like the length of like each tensor, right?
Mm-hmm.
Would it be constrained to just 32 bits because you want to store the bitmap as a float, or no?
No. It depends on how long
Okay.
it is. The way it's. Yeah, because we have to encode use 0 or 1 for every parameters, right? If there's 1,000 parameters, we have to have a bitmap with 1,000 lines. Any other questions on the pruning? I think it's simple, right? It's easy to understand. Okay. Next, calculation the compression ratio. And we know that Alex is like a 244 M the million bytes, and if 15% of the parameters removed, so this is the size for remaining parameters, and we have 1 bit for all the parameters to indicate that if this parameter is removed or not, right? And we plus them together, to sum them together, and we get this final bytes, final size, and CR is 1.134.35. Yeah, question. We know that the magnitude, if we set a bigger magnitude, will be more parameters will be pruned. Is it better to set a better magnitude? Do you think, guys, in this scenario? Yeah.
It just kind of gets at it, but I think the hyperparameterization of like the compression relies on how much accuracy you're willing to lose in your model.
Yes, yes, correct. So if we set a bigger magnitude threshold, that means the compression ratio will be higher than before, right? But it will bring a significant accuracy degradation because we removed such parameters, which is like in the original it is in the model, but right now we remove it. We use 0 to represent it. Especially in the storage scenario, we are not allowed a significant accuracy degradation because we are not to do like the fine tuning is not guaranteed. Okay, for pruning, that's all for pruning. Let's get into the quantization to shorten the bit for represent a parameter. So there are typically 2 general way to quantize a model, which is uniform quantization and non-uniform quantization. Just like these 2 pictures shows that. So the quantization, the idea of the quantization is pretty simple. It's like we mapping continuously parameter range into some discrete layer, discrete numbers. Like over here, you can see that this is a discrete y, right? Everyone will be over here, every points. But we can just mapping it into this one, this one, this one, this one. This is discrete, just a bunch of points. So let's take a look at non-uniform quantization first, because this is easier to understand. This is easier to follow. So here we have the float 32, and first we do the clustering. Clustering means that if the similar parameters, they will be classified into a same group, and the parameters within a same group has a small difference. And this is like a 1, 2, around 2, around 2, around 2, around -1, around 1.5, around 0, 0, something like that. And we can do the approximating to mapping it into a bunch of like numbers. And then last step, encoding. Right now this is floating 32 points, and we can just use a unsigned int to represent this one, which is like a 1, 2, 3, 4, only 4 numbers. We can use 1, 0, 1, 2, 3. That's 4 numbers, right? To represent it, and we need a code book to map it, to record which is which. Then this too can be represent like a 2-bit representation. 0, 0 means 0, 1, 1 means 3, right? And this is the code book. Now we finished the quantization, which is pretty simple. And this is the floating 32 bits. This is a 2-bit. We quantize the floating 32 bits numbers into 2-bit representations, and we only need a code book to translate this one. And the conversion ratio of this one would be like a 10 times 32 divided by 10 times 2 plus this codebook. This is around 2. But in reality, the parameters will be like a not 10, which will be like a 1 million, like a 1,000, 1 million, even 1 trillion. So generally, it will just float. It will just this quantization can be, the CR of this quantization can be like around 16, right?
Let's say when we look at the large enough model, the overhead of the codebook can be negligible, right?
Yes.
So what's the theoretical compression ratio for this particular example, like quantize everything into a 2-bit representation?
Yeah. Anyone has idea?
32-bit to 2-bit.
Yeah, that would be 16, right?
16, right?
Next would be the uniform quantization. But the idea is the same, but this one is a little bit complicated. And I will just leave it offline, and you guys can refer it and for further study. Okay, next, jump to our key algorithm, the ELF. For this group of numbers, do you guys see any interesting ideas, the insights on the binary representation? No? Okay, how about this group? Any other ideas? Yeah.
I mean, those all have the same exponent.
Yeah, that's right. The exponent is the same. We only do one operation, like we just mapping this group into the magnitude of 1 to 2, and we can get the same exponent, right? That's the motivation. That's the idea, like motivate us to design ELF. So the compression progress of ELF is pretty simple and effective. First, we just record the sum bit of P. P is from like a -1 to 1. And next, we get a P prime, which is absolute value of P. And in this case, the P prime is equal to P. And we get the P double prime by adding 1. And we just record the magnitude of P double prime, because this one is the same. It's all the same, and it's fixed. And we know we can just remove it, right? This is 1 bit, this is 33 bits, and we can take it together, it will be 24 bit. And we can store these 24 bits into 3 bytes. This is the compression. And the decompression is pretty much the reverse operations for the compression. Like we first obtaining the 24 bits, and we bring the exponent back because we know what number is in the exponent, and we reconstruct the P double prime, and we get the P prime by P double prime -1, and we giving the sum bit back to recover the P, right? That's it. Yeah.
Can you explain the significance of adding 1 in the algorithm?
The significance
To
of
go from
binary?
P prime to P double prime, you add 1.
Yeah.
I believe is what it said. Can you explain why that's done?
Oh yeah, it's a good question. So, if let's see, use this as an example. Here, the binary representation would be like this, and for this number is much smaller than this one, right? And the exponent which is different, even though they are from they are only 0 point, blah, 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 blah. But their exponent is different. Just because in the computer system, they represent the floating points, use like the 2 as the base. And because for this one, they has the higher precision compared with this one, because the length is long, right? And they use the actual bit, like from the exponent to represent the precision. So that's why this 2 is 0 plus plus 0 point plus blah 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 blah, but they got the different exponent. But for the 1 point, like 1.2, 1.3, 1.0, something like that, they have the same precision. So this exponent would be like aligned together. And we want to remove the exponent part for all the numbers, the magnitude within 1 to 2. So we have to add 1 in order to remove the exponent like this part, right?
Okay, that makes sense.
Yeah, that makes sense, right? Yeah.
So is this strictly based on the observation that the majority of weights in these networks lie between -1 and 1? Like
Exactly.
if there are really important weights, then you just escape those from the compression. If those weights are outside that range, and only the ones in that range get compressed.
Oh yeah.
Yeah, if you have a weight that's like greater than 1, you want to keep that because it's a very valuable weight. So that one just is escaped by the compression, and you just keep that one around and just compress all the other ones.
Yeah. That's a good question. That's a good insight. So, just like you said, if a parameter, the magnitude of a parameter is bigger than 1, that means based on our previous observation on pruning, right? This is example. This is important. We have to keep such kinds of parameters. So, let's talk about the first observation that we why we do this, because in our observation and experiment, 99%, over 99% of parameters within -1 to 1. So that means 99% we can use, 99% of the parameters we can use this F. And for like less than 1%, but very important parameters, what do? We record them as it is. Yeah, just like you said, we record it as it is because it is important. Yeah.
So is there like another like bitmap data structure that you record which one that you do
Yeah.
the transformation of?
Yeah. So, but the difference with the pruning is that we do not use bitmap 0 or 1. We use like the position with a specific position. Let's pretend this one is bigger than 1, right? Let's say 0, 1, 2, 3, and we don't use 0, 0, 1, 2. We use like a 0, 1, 2. We use 2, and this number. It's like the position as a key, and the value would be this value to represent the other parameters like beyond the -1.
So you just like a map basically.
Yeah.
Like you just record whichever parameter that is outside the range of -1 to 1, and you like.
Yeah, record
take
the
it to
position.
all.
Yeah, record the like which row like of the numbers y in which position it is outside of the -1 to 1. Because this is more efficient, right? Because we just only record several like points in comparing with the 0, 1 for all the parameters. Yeah.
Is alpha compression lossy?
Yeah.
Okay, I did, yeah, okay, I'm sure you'll cover it, but yeah, thank you.
Yeah, definitely great question. But I didn't cover it in this slides because we.
Okay. I can read the paper that's up
Yeah,
there.
you can just read the paper. We discuss about the arrow bounded lossy.
Okay, thank you.
The loss is quite small. It's like a 2 to the power of -24.
Okay.
So that's why we propose this one as like a near lossless. Okay. So, do you guys have any question about the F compression and decompression? If no, let's jump to the calculation, which is simple. And we remove the exponent, and we do the divide. 1.333, 1.454545. And that's it. Okay, quick summary. Today we reviewed and we discussed about several things. Firstly, that we present some interesting insights and observations on the massive, a large scale pre-trained model. And the insight that for like most parameters, they are within the range -1 to 1. And we recap the binary representation for floating point numbers in the computer system. And we learn the pruning, we learn the quantization, the very basic idea of pruning and quantization, and we elaborate the F, the exponentialist floating point compression. And that's the reference. Here is a quiz. Before this quiz, I'd like to, you guys have any questions? No? Yeah.
So, like in your work, have you seen that like doing like quantization, tuning, or like model compression, has it affected model performance a lot, or like how much does it affect the model performance?
Yeah, great question, great question. So yeah, this paper, the first time we submitted this paper to VLDB, and we just criticized by the idea, like we are not show the accuracy degradation for model pruning and quantization. So basic idea is that during the training or inference, like the general idea of pruning and quantization, they come up with fine tuning or retraining, because like I'm the provider, I'm a model provider, so I want to provide a model with a very smaller size, but the performance would not be down too much. So I have the data set, right? So I will just prune some more parameters and use this pruned model to train the data, to let the a pruned model to require the information from the data. And the parameters inside the pruned model will be adjusted by themselves to I should be bigger, I should be smaller, comparing with the first version, right? And after first round pruning, and we'll do the second round pruning, and follow with this fine tuning or retraining. And so in that way, the accuracy would be like a flat, and get some points, like singular points, they will be dropped down. But that point would be the limit of pruning or quantization. So in general, pruning, they can just improve 10 times, something like that, without any accuracy loss with the retraining or fine tuning. And for quantization, 4-bit would be the ultimate aim, ultimate goal. So we cannot shorten the 1432 bits in less than 4 bits without any accuracy degradation. 4-bit is the general principle for the pruning quantization use. But in the storage scenario, we do not have the data set, so we cannot retrain it. So in that way, we can only set a very small magnitude of prune without any accuracy loss. Also for the quantization, we can only just quantize the bit length slightly smaller. If it is smaller, it is bigger smaller, that means a significant accuracy degradation. But we do not have data. We cannot train it, we cannot fine tune it to improve the accuracy. So yeah. So in storage or model transfer, that's the idea, the accuracy, the relationship between accuracy and the model compression. Good idea. It's a good question. Any other questions?
So what's the storage mode between, let's say, a model stored for inference or for training within memory versus the static storage of all the binary parameters for a model in terms of, for example, a file. So what's the difference between these two different storage modes?
Okay. Let's use this as an example over here. Professor, are you asking that what's the difference between the storage or the inference scenarios for a model, right?
So when the model is stored in DRAM, let's say for model inference or model serving, like what's the difference of this storage format versus when this model is statically stored in terms of a disk file, are there any differences between these two different formats?
Yeah. There are a huge difference for several ways. First, in disk, the model is stored like a. Let's talk about training or inference. Different layers can be reused during training or inference. Let's say this one, AlexNet. During like inference or in main memory or in GPU, it will like perform like over here and over here and back to update the weights. Like these two layers are the same. These two layers are exactly the same. So during the training or inference, they just use these two layers one by one and update the weights into these layers. The shape of the layer is the same, the parameter within this layer are the same. So they have to store 2 times over this layer, but in storage side, they will just deduplicate one layer and only store this layer with a logical pointer to point this one. When this model load to GPU or load to main memory, it will be unfolded this two exactly the same layer. This is one difference. And you guys can find this idea that if you download a model and you can see the size on the disk, and when you just swap in, when you load the model into main memory or the GPU, you can find that the model is bigger comparing with the disk model. This is one difference. Another difference is on the calculation over here. So in the productive environment, if we prune this model as 0, and this 0 do not participate into this 0 multi the input to save energy, to speed up the inference, to speed up the computation in NVIDIA. So there are a lot of like technologies or schemes to find how can we prune the model structurally, like a whole layer we can just prune, a whole tensor we can just remove it, in terms of to speed up the calculation. But in the disk storage, we do not have such kinds of demand, such kind of scenarios. So we can just like by our own set rules to remove as much as we want instead of the reduce the model size. Yeah, I think that's two big difference.
So that means the memory might be a little bit bloated
Yeah.
when you store model in DRAM for model inference, right?
Yes. If,
So, for example, we have like 5 layers that are exactly the same within memory, but you have to unfold it and store 5 replicas of the same layer within DRAM,
yeah.
right?
Yes.
So, is there any technique, for example, on the fly dedupe that you just deduplicate all these duplicate the layers within memory, and when needed, we just create something on the fly. So this is different than, say, model pruning or quantization, right? So is there any technique, or are you aware of any of such kind of techniques?
I think as far as I know, I don't see any like layer deduplication in GPU while computation. But I know some for pruning, like there are some code base for different layers, to transfer several sparse metrics into a dense matrix, and use a code book to indexing which one is in that sparse, the position in the sparse, and we only use this dense matrix to do the computation, which is much faster, which is much efficient, and we can just use the speed map to unfold unfold all the results and fill up into that sparse matrix. That would be a good idea. That is a good idea for the speed map.
Yeah, and also, so for typical Python applications, right? So let's say we have like 5 Python processes running on the same computer. Like all of these 5 different processes, they share the same dependency. They all use NumPy, they all use PyTorch. But the underlying libraries, those PyTorch, NumPy libraries, they are not duplicated within RAM, right? So the operating system would just store one single copy, and that could be shared by multiple Python processes, Python applications. And this is for the sake of memory efficiency and for memory saving. And that is for, you know, some systems level trick, operating system level trick, virtual memory stuff that helps with improve the memory utilization, helps reduce the memory usage, right? It does sound like there could exist some maybe interesting opportunity where we could apply this sort of decades-old technique from this memory management domain into this machine learning model memory management. Because given the observation that the memory might be severely bloated because of these duplicates of different layers. So they are the same, but you still have to store multiple copies of the same layer within GPU memory or within the host CPU memory. So it looks to me there might exist some interesting opportunity. Right.
Yeah, I think so. But yeah, another idea I'd like to share with you on the like deduplication layers is that, for example, during the training, during the inference, like these 2 layers can be deduplicated, right? Logically, but like if they split into different stages, into loaded into different like SM, like computation cells in GPU. If we just deduplicate one of them, and the pipeline would be incomplete. So we have to like dynamically download this duplicate for like here to do this part of the computation. But it will be like time consuming.
Yeah, I see your point. So,
Yeah.
So maybe during the training or inference, so the feed forward or the forward propagation, the same layer will be updated differently, right?
Yeah.
So that means different layer is not only read but also it needs to support update operations. If this is the case, we cannot just apply deduplication, right?
Yeah.
And this is different from the shared library memory. Because those shared libraries, they are just binary code instructions. Those are immutable. Those are read-only. So that is why there's opportunity there, but might not be the same opportunities here in this completely different scenario.
Agree. But inference would be a good scenario. Inference would not update the layers.
Right. Yeah.
Yeah.
Sorry, but what was there? It's not obvious to me that well, I think you said in your talk that the rate of duplication in the layer space was something like less than 5%, or something that order. And GPU memory is very taxed, I understand. But is that the kind of? It sounds like that would be the theoretical limit that this kind of deduplication at the time of inference within memory would be able to catch you. Is that accurate to what you're suggesting?
Not exactly. So that 5% something is actually for the static data when the model is dumped as a on-disk file. So those duplicate layers are all automatically deduplicated.
I
So
see.
that is all the unique data that is left there within the file. But when everything is loaded into memory, it gets unfolded,
Okay.
gets replicated. Yeah.
I see.
Okay. I think this.
And also maybe we can have a short discussion about maybe the pros and cons of the L compression and decompression algorithm. So what do you all think about the advantages and maybe disadvantages of this particular algorithm?
Yeah.
straightforward.
Yeah.
Yeah,
This
simplicity
is
is a
particularly difficult to implement.
Yeah.
Which is just good for, you're not adding a lot of overhead in whatever, like, actual, like, programming and logic is required to execute this. Like, this seems really efficient for sort of the situation where a model really needs to be, like, distributed across a lot of devices, and, like, if people need to be, like, downloading these things to just, like, use on specific devices, it seems really easy to implement and save a lot of space for that. That's really the big upshot of all of this.
Yeah, yeah.
We were talking about the trade-off in pruning between accuracy and compression, and I think this algorithm to me seems like it's leaning more towards the side of maintaining accuracy. Like the compression ratio is somewhat limited in like that you can only get rid of those 8 bits for each float 32 that you have, but you're maintaining most of the fidelity of the original numbers that were in the parameters.
Sure. Yes. Yeah.
So is that a sort of like a downside or?
I would say that's an upside, but it depends on like if you were on a mobile computing space and you had like very limited compute ratios available to you, maybe you would want something that had more compression. At least for I guess that's more of an inference state, but still it depends on your application, I suppose, whether that's a benefit or an upside or a downside.
Yeah. It's scenario specific, right? Yeah. Sometimes for mobile phones, they might not be stored such kinds of many like models,
Mhm.
but like for multi-use the IoTs, like watches, like the sensors, they might need to store different models for different works. So in that way, the ELF can be performed, right? Yeah.
So just thinking about like the usage of like model compression. So like I guess aside from like something like transfer learning, or maybe some other type of like machine learning, I guess, paradigm. Like what else can compression be used for? Or like in what scenario would it be helpful to compress a model?
In storage side.
I was just thinking like if you like the goal of compression would be like you have a smaller one.
Yes.
So like if you do something like transfer learning, it's easier for you to like
Yeah.
send like distribute your model to like other people. So like what are there any other I guess usage or like advantages for compressing?
Yeah, this is just like you mentioned in the transfer learning, like or the fiduciary learning, they have to transfer model very rapidly, right, and very often. So this would be a good scenario while maintaining the model accuracy, like the pruning and quantization. And other ones like right now, it's like the error is can be calculated for every parameter. In that direction, we can do some like research or improvement, like adding privacy to while compression, because we can manipulate the bits during the compression, and we can just flip it 1 to 0, 0 to 1 to control the error, to control the distribution of the noise added to the model, and that would be a combination with the compression and the privacy and security. And also, this ELF is not only used for model. It can be used for any like floating point numbers with any like a -1 to 1 distribution. Yeah, for the simple side, I think the pruning, the magnitude pruning, right? You guys already got the idea, like find the smallest one and remove it, which is simple, it's like stupid. But this one, simple but effective. This one has been widely used in the last 5 years on like almost the big tech companies for the like magnitude pruning. It seems like very simple but effective, and I think ELF would be in that direction, simple but effective. And also another feature is that can be parallel, can be embarrassingly parallel because you can. Oh, it's not. You can just chunk the whole parameter into different small subchunks, depending on the hardware or the cores you have to do the multi compression, which is really fast. And in our paper, in our experiment, we use like a 52 core to perform the ELF, which is 4 times faster than the parallel zip or the general purpose compressor. And which you can, if you refer the picture, which is the gap is huge comparing with other compressors.
So why general purpose compressor like the GZIP or TAR, they are significantly slower than this inversely parallel algorithm?
Like for me, I think the ELF can be used on like a even single one parameter, but the general purpose they have addict. They have to slightly to scan the data and use addict to record which one is repeated and using the index to record that one, which is smaller, which is slower because you have to do that one. But in ELF, we can just cut it and get it in and get out. That's it.
Can you define embarrassingly parallel? I'm not familiar with that term.
It's like, correct me if it's wrong. Yeah.
Right.
It's like embarrassing parallel is like we can do it in parallel. The defining of the parallel. Parallel is like right? Embarrassing is like just like that, and we do not need any like logical, any like organization, any reorder things. We just do it.
I see.
Yeah.
So it means that you can directly split the tasks into separate processes. There's no like overhead that has to be used to logically
Yes.
combine these parallel processes. Into
Yes.
Okay.
No overhead to combine it. No overhead to like to reorganize it, to reorder it. No, we don't do that.
So in other words, if you model this as a DAG, it just be one starting point and one end point for each partition. And there's no interdependencies here and there. Each one is independently processed.
Okay. Let's show the demo. Okay. I'd like to show you guys a demo on ELF, which is quick, is simple. Okay, done. You can see that here is we download a model names this one. This is an NLP model, and the original model size is 200 and is around 300 megabytes. And this is the ELF compression, and this is the compression ratio, and this is a compressed file. We do it parallel. I use C++ pthread to parallel it. So okay, for the reference, you can see that this is the original model. Over here is around 300 megabytes, and that's the compressed file. Over here, that's the result for parallel, which is 222 megabytes, comparing with the original around 300 megabytes. And the core code would be only this function, the ELF function 32, only this one. Oh, it's smaller. I think it's small. Okay. Can you guys see it? only from here to here. First, we just get the sun, and we obtain with a p prime, which is a absolute value of p, and +1, and record the mantis of it. This is a bit operation, which is quick comparing with the arithmetic. And this is 24-bit, and contact the 1-bit, sun bit, and 23-bit together, and save it to appending this one to the bit array, and save it as 3 bits. That's it. Oh yeah.
Can you go back to the code you just showed? Yeah. Is there well, I guess in your research, is there like a number for the limit max apps?
This one?
Yeah. Is there a number that you use? For
Yeah. 0.9999.
Okay.
Yeah. Just for in terms of overflow, I don't use one because the number cannot be precisely presented in computer science, in computer systems, right? So I use 0.9999 in terms of the overflow. Yeah. That's it. So it's a quick quiz. You guys can find the quiz on Google Form. I think. Yeah.
I got 7 more. You get yeah, I mean, I just did like 90 times 4, and that was 360. He never said, I don't think, how much 460 is worth. That'd be 20. I'm assuming they're worth 20 because they're half of float 32. No, 32 is times 4 from megabytes or whatever.
Could you unplug it? Yeah, dude. Are we trying to leave?
I don't know.
Is this done? I think so.